So we memorized the derivative of sine and cosine. We've even used it a little bit. Now we're going to use it some more. Oh, yeah. Sounds fun. So if sine of x is f of x, find the following. A, the slope of the graph at 0. Slope of the graph at 0. So again, it's reading the instructions and knowing what to do. The doing it is not really the hard part, but the knowing what to do is what we need to do. So, any strategies here? What are we going to do? Peter, you're turning around because you know what to do? So what do we do? Yeah. Slope at a point. We're trying to find the slope at a point. And by point, we mean an x location. That is the derivative. So, can we go straight to f prime of 0? That's what we're after, right? No, we have to first find what? French? All right. So f prime of x. F prime of x is what? The limit as h goes to 0 of... Oh, it's just cosine. Oh, that's good to know. That's a time saver right there. And now I just plug in a 0, so that's cosine of 0, which is 1. How's that? Beautiful. No, it's not beautiful. 1 does not equal f prime of x. That's f prime of what? You fell into the trap. I dug a big hole and put like palm leaves over the hole, and you didn't see it. You fell right in. This is f prime of 0, which is cosine of 0, which is 1. You would lose a point if you misuse equality. Mathematical prevarication. All right, so let's see what that means graphically. If I look at the graph of Sahala, oh, I got the new colors. Let's slide over. Oh, let's use periwinkle. Yeah. Oh, man. I'm good for the rest of the year now. Blue satin. Okay. Or how about turquoise tangent? Which is turquoise? The one on the right column? Third column, second color. Isn't that green?
Second column, third row.
Second column, third row. Okay. So if we're trying to find the tangent line at 0, here comes turquoise tangent.
That's pretty good.
If you hold it, look at that. And then you can kind of move it around. Oh. Oh. Oh, nice. Okay, so there's turquoise tangent. And, of course, I drew it wrong. But if we were interested in how fast the sine graph was launching out of the origin, at that instant, it would be going up 1 unit for every 1 unit it's going to the right, which means the slope of the line would be what? Yeah, and what angle, sorry, would this be? My bad. 45, yes? So when we get to optimization, we can look at this problem. If you're trying to like chunk something as far as possible, the optimal angle to achieve the maximum distance, of course neglecting air resistance and birds flying by and taking the object you're throwing, is 45 degrees. It's the optimal angle. So sine launches out at the optimal angle. But in the very next instant, that tangent line is what? Less steep, and it approaches what? 0. Yeah, so the slopes are decreasing. Right there at 1, right there at 0, sorry, it's 1. Okay, now f prime of 7 pi 6. Let's see if we can predict it over here. Where's 7 pi 6 in relation to the full cycle of sine? Yeah, just below that. That's pi, so 7 pi 6 is going to be something right around there. So let's try it again. Oh, man, you can kiss for a lot longer now as you put it into place. I'm liking this new notability. So a reasonable magnitude for that slope would be what compared to 1? Steeper or less steep? It seems like it should be less steep, right? So, and it should be positive or negative? Negative. Okay, so let's see what it actually is. F prime of 7 pi 6 is nothing more than cosine of 7 pi 6, which of course we know is what? Negative. Square root of 3 over 2. Yeah. Which, does anyone know what that is? Is a decimal approximately? Negative 0.8-ish. Yeah. Yeah, 8-ish. Yeah, it's exactly what it almost is, kind of. So that makes sense, though, because the magnitude is 0.8, which is less than 1. Find all the x between 0 and 2 pi where the graph of f has a horizontal tangent line. Well, again, we don't really need calculus for that, do we? Horizontal tangent line. I almost feel like I need to use a different color. So here's one. Hold it. Here's another one. Oh, I missed it. No problem. Oh, boy. You can, oh, look, and it actually locks in at horizontal. And at vertical. Oh, that's so sweet. Look at that. There you go. So there, do it again. There you go. So where do we have the horizontal tangent lines between 0 and 2 pi? Well, the first one will be at the local max, which is also the absolute max. That's at pi what? Halves. And then the other one over here would be at 3 pi halves. Now, that's getting it from the graph because we know what sine looks like. But again, here's the power of the calculus. If you want to know where the horizontal tangent line is, that is the derivative, f prime of x, and you set it equal to what? What's the slope of a horizontal line? 0. Okay? And of course, that's cosine of x. That's f prime. It equals 0. By the way, you would get a check for setting the derivative equal to 0. And now it's what time? Look at your watch, 12:54. You know what it means? What time is it? Unit circle time. That's right. So where is cosine equal to 0 within one rotation? Cosine is equal to 0 when x is 0, which is up here at pi halves, and of course, all the way down here at 3 pi halves. So I do this problem so that we can compare the results and get the same answer. That way you'll have full faith and confidence in the power of the calculus, and you won't really need to verify it anymore. And of course, we can find all the ones that are coterminal with that. Pretty neat little application. I'm really liking the new turquoise tangent. Yeah. Okay. Here's an application of the power rule of which Newton would be proud. Motion. 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 All right, so just to kind of reinforce it again, the derivative of a function gives us two equivalent things. The slope of the tangent line at the point. Whose perspective was that? Leibniz. And the instantaneous rate of change at that point, well, that would be the pre-Newtonian would be Galilean, but then Newton came up with the calculus. But Galileo was also working on the motion. So yeah, kind of a precursor to Newton. Newton actually said, if I have seen further, it's because I was standing on the shoulders of giants. And of course, Galileo was one of the giants to which he was referring. Some people who underachieve then say that if I have not seen further, it's because giants were standing on my shoulders. So anyway. Get off me, dude. I can't see. All right. So if we let h of t be a position function, where t is a time, and v of t is the velocity function, that would be the rate of change of the position instantaneously, and a of t be an instantaneous acceleration function of time. You can relate those instantaneous functions to each other in the following way. First of all, let's look at this. If we have an instantaneous height or position, that means plug in any value of single t and find the instantaneous position. That's not a breakthrough, that equation. But then this would be v of t, that's an instantaneous velocity. Plug in a single value of t and find the velocity at that moment. And then, of course, the a of t would be the acceleration, instantaneous acceleration. Plug in a single t, get out an acceleration. These three things are all related to each other, and you can relate them to each other in this equation, okay? Now let's start with this right here. V prime of t is equal to a of t. That's how you read that. So what does that mean? That means if you're talking about how fast someone's velocity is changing at any particular moment, you're talking about is what? Acceleration. Wow. Look at Usain Bolt go. His velocity is increasing off the line. He is accelerating. And because we're talking about instantaneous rate of change, we can say that v prime of t is equal to a of t. But, backing it up one, if you were talking about how fast someone's position was changing, that is h prime of t, wow, look at his position change. His position changes rapidly with respect to time. You're talking about his what? Velocity, yeah. So this would be kind of the intermediate equation. H prime of t is v of t. That is the rate of change of height if something's falling, or the rate of change of the position is velocity, instantaneously. And the rate of change of velocity is acceleration. Yes, so now we can relate them all to each other by using this notation here, and we do read that as double prime. So h double prime of t is v prime of t, which is equal to a of t. So it's essentially this. If you start with your position function, take the derivative, right? And you get your velocity function. Take the derivative of that, and you get your acceleration function. So this is called a higher order derivative. The order of the derivative for the first derivative is 1, and then the second derivative would have an order of 2. And you could keep going. What would you think the rate of change of acceleration is? Wow, look at his acceleration change. His acceleration is increasing. That would be hard to comprehend. Let's think about in terms of units, because this is nice to tie it in as well. If I have the position function h of t, let's say I'm measuring the position in feet against time in seconds. Then if I take the derivative, I get h prime of t, which of course would be v of t. Well, whenever we take the derivative, Leibniz notation comes in, and remember it's dy dx, or in this case it would be dh dt. What's nice about Leibniz notation is it preserves the ratio. Remember, the derivative is the difference quotient as the points get infinitely close to each other. So it is a quotient. So what would the units then of the derivative of any function be? It would be the units of the y divided by the units of the x. And what's feet divided by second? Feet per second. So now the velocity would be feet per second graphed against seconds. And if we took the derivative of the velocity, v prime of t would equal a of t. What are the units of v prime? Well, it's units of y, which are feet per second, divided by seconds, which gives us what? Feet per second squared, which is velocity, acceleration, the rate of change of velocity. And we graph that against seconds. So those we have pretty much an intuitive understanding for from our physics upbringing. We have feet per second, and feet per second squared. Okay? Now, when you say feet per second squared, if you tie a number to it, you could say, ooh, his acceleration is 3 feet per second squared. Or you could make it a little bit more meaningful and say his velocity is increasing by 3 feet per second each and every second. That's another way to look at it. So let's just go one further and see if we can make sense. If I then take the derivative of acceleration, I get some unknown function. Well, what are the units of the derivative of acceleration? Feet per second squared divided by seconds, and that would be feet per second cubed against time. Do we have an intuitive understanding of what that measures? Not really. So if you back it off, instead of saying feet per second cubed, maybe say feet per second squared per second. It means the same thing. So that would be the rate of change of acceleration. And I use this analogy every year, so if you heard it last year, remember, that's great. If you ever are at a red light and the guy pulls up next to you, and he looks over and he starts revving the engine, that's not you, right? He wants to race off the light. So you rev back and then you let him have his little glory, whatever, and then you get to the next stoplight, and then you're even again, and you're like, oh. Anyway, he accelerates. What if he has like a little transmission problem as soon as he's accelerating? His velocity is increasing. He's accelerating, but he has transmission problems right in the middle of the acceleration. It's going to kind of decelerate and then accelerate. What's that motion called? It's jerking, right? It's jerking. If his acceleration is changing, whether it's increasing or decreasing, it's going to jerk a little bit, and that is a function in physics, the jerk function. That's what we call it, the jerk function. And so it's a good way to remember it because that guy next to you that's revving his engine, there you go. Very good. Very good. The jerk function. We're not going to work with the jerk function here, but just kind of an FYI. And what would be the rate of change of the jerk function? I don't know. You can keep going. Mathematically, you can keep going. String theory has the possibility mathematically for many, 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 many different dimensions, although physically we can really only comprehend 3. So it's like, what would be the 4th dimension? Is it time? No, not really. What would be the 5th dimension? I have no idea. But mathematically they exist. So anyway, example 12. We have time for example 12. Oh, yes, we do. Get this. This is like an old problem. This dates how old this is. Look at this. A calculus textbook. What is that? What does a hard copy of a math text look like? Haven't seen one in a while, huh? Well, when you go to college next year, if you have to take Cal 1, you probably have to buy a textbook, and it's probably going to be somewhere in the neighborhood of $150, $160 if you're lucky. Maybe you'll find a used one for $80. Sometimes they're over $200. Yeah. So anyway, but y'all are not going to have to buy one because y'all are going to pass the AP Calculus exam and get credit for it. So anyway, a calculus textbook is stolen from a museum. Ooh. And it's taken to the top of a 400-foot tower. Why? For no good purposes. That's why. These people, these thieves, plan to drop the textbook down to the unforgiving pavement below, just submitting it to brutal torture. Okay? They're taking out their math anguish on the innocent book. The height of the book, h of t, in feet at any given time, t seconds during its brief but painful plummet to earth, is given by the equation h of t equals negative 16t squared plus 400. Answer the following questions regarding the book. Now, let's see where this question comes from. In physics, you memorize your kinematic equations for falling objects near the surface of the earth, right? It's negative 1/2 lil g t squared plus v sub o t plus h sub o. Maybe you memorized that. Lil g can be measured in meters per second, which is about 9.8. Or for AP purposes now, y'all use 10 because you can do more calculations without a calculator. It's also about 32 feet per second. V sub o is your initial velocity. So if you're throwing the book down instead of just dropping it, that would have a value. And h sub o is your initial height. So that's how this comes into being. We're using feet per second, so we use 32 for little g. That's how we get the negative 16. What's the initial velocity if we're just dropping it? 0, so that term goes to 0. And the initial height is the top of the tower, 400. So anyway, you get these kinematic equations. In physics, then, you have to memorize the velocity equation, but you don't have to anymore because h prime of t should be v of t. And if we take the derivative of the equation above, using the power rule, what is 2 times negative 1/2? Negative 1, so we have negative g t to the first, plus, what's v sub o times t's derivative? That's a linear term, right? So that's t to the first, so any linear term becomes just the coefficient, v sub o, and h sub o is the constant. What's the derivative of any constant? 0. So here would be your instantaneous velocity function from physics that you have to memorize. And then, of course, h double prime of t would equal v prime of t, which we call a of t. And let's see what that is. What is the derivative of negative g, the constant, times t, the variable? Negative g. And then what is v sub o's derivative? 0. So look what we have here. We have the acceleration of a falling object near the surface of the earth, neglecting wind resistance and birds flying by, taking it out of the air, and all the other shenanigans. The acceleration due to gravity is known as just negative g, the gravitational constant. Okay? So where did these equations come from? How did they come into existence? Did they fall out of the sky like the apple on Newton's head, supposedly? No, they were actually derived going backwards. Little g was an empirical constant that was observed, and then by doing what's going to be called anti-differentiating, or solving differential equations, they went backwards from the acceleration constant to the instantaneous velocity, and then worked backwards from there to the position equation. But right now, we're learning to go forward, because it's a lot easier to go forward than to go backwards, right? And if you don't believe me, just try driving home that way this afternoon. Okay? It's a little harder. But still don't speed. Okay. So let's go ahead and look at our specific problem. For how many actual seconds was the book falling? How are we going to do that? Calculate solve for t? What? That's vague. I don't get it. What? Oh, thank you. I want to know how long it takes for the book's height to reach 0. So I want to set h of t equal to 0. Look, I'm writing in burnt orange. I kind of like that. Yeah, Halloween. Okay, that's what I meant. Negative 16t squared plus 400 equals 0. Yes, and then it is a difference of 2 squares. So if you want to factor it into 20 minus 4t, 20 plus 4t, that'll work. Kind of like that, actually. Or you could separate the variables and divide. I'll go ahead and negative 4t plus 20, and negative 4t, or it'd be positive 4t plus 20. Does that do it? That's kind of a funky way to factor, but it works. Negative 16t squared plus minus plus. Yeah. So now if you set them each equal to 0, of course you don't have to. You could do it in your head. You get t equals 5 or t equals negative 5. Now the quadratic, of course, has two roots, two solutions. But in our problem, we have a relevant domain, and the time starts once we let go. So what do we know about the negative one? Can't work. So let's go ahead and declare the answer. So t is equal to 5 seconds. The book was in the air for 5 seconds. That's a long fall. How many seconds did it feel like to the book? Yeah, that's the answer. Forever. Or just infinity, right?
You felt the wind through.
That's right. And it enjoyed it. Or girl, could be. All right, so anyway, 5 seconds. What was the velocity of the book in feet per second the instant it hit the pavement? That's an instantaneous rate of change. A lot of people say 0, right? But that is not correct. That's its instantaneous velocity, the immediate instant after it hits the pavement, not as it hits the pavement. Okay? Well, how are we going to do that? How long does it take to hit the pavement? 5 seconds. So we want to know its instantaneous velocity at 5. So I need an instantaneous velocity equation. Galileo couldn't get it, can we? Yes. So h prime of t is going to equal v of t, which now the derivative of negative 16t squared is just negative 32t plus what? Plus nothing. And so now we carefully plug in v of 5 equals negative 32 times 5, which gives us what? Negative 1, 6, 0. And what are the units? Feet per second. Not meters, feet. Yeah, feet per second. That's pretty fast. Now, what does the negative for a book? What does the negative mean? The velocity is downward. Because what it literally means is that the height is decreasing. That's what it literally means. The height is decreasing by 160 feet per second. Because you want to interpret it as a vector. But of course, the negative is just directional as well. And it means the book is falling with a speed of 160. At this velocity, what happened to the page in the book discussing the squeeze theorem? It got squeezed. It got squeezed. It got sandwiched. Yeah, there you go. The guy who writes these problems. What was the average velocity of the book in feet per second during the duration of its free fall? Now, notice what type of velocity it's asking us? Average. Do we need calculus for average velocity? No, because what other word starts with average? Like algebra. Good. So for average, you don't need calculus, you need algebra. Average velocity is nothing more than the change in the position during its free fall. So where its final velocity or its final position minus its initial position all over the change in the corresponding time. Yeah, what do we call that? The DQ, Hunger Buster? The difference quotient. We're measuring height in feet. We're measuring time in seconds. Look at the units. Feet per second. So this would be the slope of the secant line from the beginning to the end. So average rate of change, just algebra. Now, we know what that is, right? It fell 400 feet in 5 seconds, but it would be negative 400 over 5. So we end up with what? Negative 80 feet per second. Now, does that mean it was falling at 80 feet per second the entire time? No, that was the average, right? Like if you let go of it and it hit 80 right away and it had it on cruise control the whole time. Can books do cruise control?
Yeah, some.
Yeah, some, right. They're really expensive books. This one started at 0, it ended at negative 160, so it wasn't going negative 80 the whole time. But did it have to be going 80 feet per second at least once during its journey? Yes, that's kind of like the IVT for derivatives, isn't it? It's called the MVT. Ooh, that's coming up. Yeah. Yeah. What was the acceleration during its fall? Last one. We need an instantaneous acceleration, so we'll come down here. H double prime of t or v prime of t I'll call it A of t again, just reinforcing it. And it's what? Negative 32, the constant. So notice, because it's a constant, you could say that it was 32, or the velocity, what was the acceleration? How about this? Negative 32 feet per second per second. There's going to be a difference as we move forward with a numeric answer versus like an interpretive answer. Negative 32 feet per second or per second squared, either one works here. I took the derivative of the negative 16t squared in the beginning, and that gave me a negative 30. Negative 2 times 16 is negative 32. So you multiply and then subtract. Okay? So that means for every second it fell, it gained another 32 feet per second in velocity units. Okay? All right. We'll pick up there tomorrow. Hopefully we'll finish. I think it's going to be pretty easy. We've got 2 examples. Worksheet will be due on Thursday. Hooray.